The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show.
Today we have some special guests from MathWorks. They're going to show us how to use MATLAB and Simulink to work on our mini pinball kit.
Let's get started.
Amazing hacks.
Should we take it for a spin?
Inspired designs.
Imhotep's priests.
Regrettable acting.
No one seems to get it.
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Who are you?
Yeah, hi Ben.
How's it going?
Very good. I'm Terry Dennery of the MathWorks.
Oh, good to meet you.
Hi Felix.
Hey.
It's good to meet you.
Oh, you too.
So what do you do at MathWorks?
Well, I'm what they call an application engineer.
Okay.
All right? And really what it means is I fly all over the United States. I meet with engineers who are interested in using MATLAB and Simulink.
Oh.
These engineers typically are building electromechanical systems.
We do that sometimes.
You do, and your pinball machine actually is one of these.
Like our mini pinball machine.
Okay, and what really interests me is that there can be very interesting software that's going to essentially make that pinball machine work. Okay, and that's really the forte of what we do with MATLAB and Simulink, is develop that kind of software.
And Felix, you have a mechanical rig over here ready to go?
Yep, I got the buttons and the flipper all set. We just need to test out the 3D model and then make some code for it. But first, maybe you could show us how to use Simulink and MATLAB.
I'd love to.
Terry asked me to create a 3D CAD drawing of our pinball machine that we're trying to build. So I drew that up in Autodesk Fusion 360 and I sent it over to Terry, and it looks like you've done some sort of simulation here with it.
Yeah, so let me show you where I ended up.
All right.
Yeah, basically you can see the orange ball and then you can see the little flipper go. All right, and you essentially see where the ball's going to bounce. What I think is that we've been able to do real well with our stuff, MATLAB and Simulink are essentially tools for analysis and simulation of electromechanical systems.
Okay.
Right? The real premise of all this is anything you do in simulation is never as good as the real thing.
So would it be possible to feed pulse width modulated signals, or at least a representation of them, from our microcontroller into the software?
Absolutely, and that's what we call hardware in the loop simulations.
Okay.
Right? And one of the key things to doing that properly is that your processor, from the MathWorks point of view, is hardware. And the thing about hardware, it's got no choice but to run in real time. All right? And so what you end up having to do...
You have to deal with the operating system and the COM ports?
Well, absolutely, we do that. But also, we need to enforce real time. All right? And that our simulation needs to be timed by your board, not by its own processor.
How do you force real time on Windows 7?
Well, the first thing we do is we don't use Windows 7. We have our own, we call it Simulink Real Time. But essentially, it is a real-time operating system.
Your own operating system.
Yeah, and we sell these little boxes because there aren't a whole lot of computers out there that are really kind of suited to really employ it. And so we sell these boxes, which basically are processors that have direct connection to the various, I'll call it hardware transmitters, maybe. Things that you can essentially connect your devices to.
Right.
All right, and we essentially prototype the algorithms. We hook up to all your instruments, like your actuators, your motors. In the case of this, one real interesting sensor we might put together is an image system that's going to really kind of track that ball. And I could see us coming up with an algorithm that says, move that flipper exactly when you need to get the ball.
It could play itself.
It could play itself.
We should probably explain in a little bit more detail. So the reason why I was talking about a real-time operating system, your Windows, Linux, Mac operating system is doing all sorts of things in the background that you have no idea about. So even things that seem instantaneous aren't. A good analogy is like, oh, look, it took 3 seconds to open my browser. Well, there's a reason why that happened. And if you're trying to do low-level analysis of things that are being controlled as fast as a microcontroller can do them, you're going to miss some stuff. Yeah. Or there'll be a lag. Like, now I'm going to look at the serial port buffer, and now I'm going to get that data. Yeah. Oh, look, 300 milliseconds has passed.
So, Mr. Terry, can you show me some of the 3D modeling that you were doing on here?
Okay, so here's basically kind of the end point. We end up at this simulation.
Okay.
of the pinball machine. We got the ball, we got the flippers. Flippers are moving in a way to essentially...
Super cool. You have a script making the flipper go, or you're telling it what to do?
I'll tell you what I did. Right? Essentially, it is a model of the real physics, which means that we're defining initial conditions, and then we're just letting it go. You'll see kind of initially it's on a trajectory up. So we initialized its velocity at that point.
So it starts where something's happening.
But then it encounters a wall and says, oh, I got to bounce off that wall. So we put stuff in that will essentially model that collision, right? And it goes through a few collisions before it ever gets to that flipper, right? And here's really what I did, okay? You'll see that at that point, and what is that at? That's about 2.7 seconds. That I realized, the ball's about to hit the flipper. Why don't we make the flipper go then? Essentially, I ran the simulation to figure out when the ball is going to hit the flipper to good position. I said, okay, let's use that as a point where we drive the motion of the flipper. And so we set that up right there.
Okay, yeah, at a time?
Starting at, it turns out, 2.78 seconds. And showing this to Ben earlier, he said, you know what? 5/100ths of a second probably is a little bit fast for that flipper to move. And we could change that if you want, but I think it's kind of neat where it is right now because it hits it real well. And if we slowed it down like in half and reran the simulation, I don't think we'll find it having quite the shot it did here. So this is still the recording where it ended up in that corner. Hit the recalculate button now.
It has pretty much compiled a new...
Yeah. It's all done already. You can kind of see that and see kind of that slower punch did not get it nearly as far. So anyways, you want to kind of see how we brought this in?
Sure.
Okay, so Ben sent me a model that he drew up in Fusion 360 created by Autodesk. And so I told Ben, give it to me in one of these formats, Can you give it to me in Autodesk Inventor? Okay. Can you give me in Pro E, CATIA, SolidWorks, whatever? And we found that STEP was a good file format for him to give it to me. So I bring that in like that, and there's that STEP file. So it's filtering on that, and I bring it in. Okay. And so that is the geometry created from a CAD tool. You can kind of see from these lists here the various number of parts and the assemblies that he created to do this. All right, and if I hit run, and this tool's got a run tool too, I see there's absolutely no connection, and it's really just a bunch of free parts, and that if I hit run, it's a free fall. All right, and so now what I'm gonna do is I'm gonna fix that part. I think what I'll also do is let's make this a different color so we can kind of see the difference between other parts. And so those flippers are really kind of the parts that we haven't really done too much yet with.
I see.
All right, and so we see the underside. We don't see the solenoids yet, but there are solenoids that are going to fit in there too. And I hit run, and I get to
see
there.
you later, flippers.
So the idea is really let's define, the motor. And the motor's, it's really doing two things. It's holding the parts together, so it's very much like a hinge. But it's also a hinge that you can exert a torque through to make things move. And so we're going to begin on kind of the hinge part. And this is the part that I really like about this tool, is the three-dimensional user interface, right? And I can zoom in, I can rotate the view, and then I can point and click, and I can say, that's where I want my joint to be, right? And we've been talking a little bit, I think, so far about the fact that mechanical connections are defined by point location, and that's a little bit of an idealization, but as well as orientation, we got to tell it what's the direction of movement. In this case, we want it to rotate, and we want it to rotate about this axis perpendicular to the surface. And so I'm putting this X, Y, Z in there. We see that the Z is the axis that's sticking out of it.
Is that locking to anything? Or you're just saying
I'll show you what
that's
it is
like
at
the
this
best
point.
location for it?
It absolutely is locking to something. So I'm going to hit run just so you can kind of see this. But notice it's moving with that part that I connected it to.
How did it know that that's where you wanted it?
Well, that's because, again, these 3D tools are pretty impressive in how they manage geometry. And so as soon as I click on that, it finds every circular edge there is.
Okay.
Also finds every corner. It finds every surface.
I see.
And so anyways, I'm going to...
It just figures it out.
Yeah, and as soon as I hover over a circular edge, notice the mouse changes. It's got that big bullseye. And so I click on that, puts it right at the center. All right.
Very intuitive.
So let's put the hinge part in now. All right. And so I'm going to select on that. So that's a part. You can see it right there, the flipper bat.
Okay.
Now this part that represents this overall assembly, that's called the PF and fingers, and it's that part right there. See the little anchor on it even indicating that we've frozen it. So what I'm going to do is I'm going to click on that, click on this, and I'm going to create a joint. Right? And it knows that that frame is on the part that we've connected to. And so very rapidly, you just can go here and you say, make that a revolute joint. I hit create, and I get this little green cylinder thing there. All right, and we see it's flopping around, therefore it has defined the axis, all kinds of stuff like that. All right, now the next thing I'm going to do is I'm going to turn that into a motor, right? And so selecting on that little green object, I choose motor. And what do I want to call this? I'll call it flipper bat motor. I want to get at one more aspect of this, all right? And I want you to keep your eyes on what's happening below, all right? And that stuff's just falling, okay? It's because we worked with those individual parts, right? But I'm going to fix something in this drawing, is that flipper bat should be part of that assembly right there.
Oh, so then it won't fall through.
And so what I'm going to do now is I'm going to treat these assemblies as if they're all one piece. Yeah, right now we're just driving them. We're not too worried about, how they're moving yet. In a way, that's why you want to get it into MATLAB and Simulink, where you have a lot of control to essentially make it move exactly the way you want it to move. And it's that ability to mathematically express things that's available through Simulink. So anyways, here's the thing I wanted to show you. All right, check the underbelly right there now. Yeah, it's just falling freely. We haven't paid attention to any of that so far. So at this point, we really focused on 3 parts, the board itself and each of those 2 flippers. But you can see there's always 6 other parts that are represented by these things. Now, the flippers, it's called the flipper bat actually, those are the pieces. You can see them kind of highlighted by those frames right there. These bats are part of these bigger assemblies. And what I want is, I want these to move as if they're one body, okay? And so I rigidly join these things as if they're all one part. And so what I'm going to do now is I'm going to introduce my own little assembly. All right, I'm going to include everything except for the flipper bats. I'll call this the rest. And so we'll anchor that, and hit run. And that's enough for what we want in Simulink. And
Right.
what it really means is that we have 3 main parts, the flipper, each flipper, and then the playing field. And so at this point, we do have the ability to bring this in. Let's go ahead and do it. So this is a MATLAB script. All right, it's called Get Geometry 1.1. And basically this is the model, and I'll hit run. And so now I pretty much got everything that we just put into it. Now with regard to the model that we put together for you, you know what the hardest part was? And this is what it looks like underneath the hood, is that there are, well, and you can kind of count them right here, 1, 2, 3, 4, 5, 6, 7, 8. 8 surfaces on the playing field. There are 4 surfaces on each paddle. All right, and this is purely in 2 dimensions, because you remember your paddles are essentially a circle, 2 straight lines, and another circle. That circle and the 2 straight lines and the other circle, they all need to be represented. And what we did, really was kind of came up with some methods for how we're going to model the collision. You and I in the break were talking a little bit about this, but how do you model collisions? We know kind of physically F equals ma. We love things that trace back to that. Force is equal to mass times acceleration. And so it really is about how do we represent the force between the ball and the paddle during a collision. And so the choice we made here was really, let's say it's like a spring, and that spring really doesn't start getting compressed until that ball actually reaches that surface, right? And so then as it gets compressed, of course, it's applying quite a force onto the ball, and so therefore it's slowing the ball down quite a bit. And after a while, it actually reverses the direction of the ball, and then sooner or later, it's off the ball. If you're really interested, I'll go just one step further and show you what that looks like in Simulink speak. Okay, and that's a spring damper.
Oh, so this is inside every one of those blocks has...
Yeah.
Okay.
Has essentially the formulation is represented by this.
So probably all the surfaces, this is pretty much the same, right?
All the surfaces, absolutely, they're the same. I can tell you.
Unless it's like configured to represent a different type of material or something.
Well, even that, there was this very useful reproducibility. So basically we did this once, and then we just copied and pasted in all the right places. And then we set up a parameterization on this, which allowed for things to vary for all the different interactions we want to account for.
So this is quite literally object-oriented programming.
I think Simulink absolutely is object-oriented programming. And it's kind of neat for you to kind of recognize it, because we don't talk about that much, and I think that both are certainly cool things, but maybe they're both cool things for the same reason too. I certainly think that our ability to draw a picture in 2 dimensions and show connectivity of objects is a particular strength of Simulink and in general the block diagram format. So Ben, I think Felix could be excited about this. That we were kind of talking about this idea earlier, but we hooked up a game controller to my laptop. What's that? It's USB connection, right?
Yeah, we don't have the dongle for this one. So these are digital inputs from the controller.
Can you push the right button?
Yeah, so nice. See how 0 to 1.
Yeah, and now push the left button. Okay.
So what's the next step?
Well, I think the next step, and I'll kind of, it may be easy, may be hard, but basically we want an input into this block. And so right now, this is simply a hard coding based on the clock. You see the clock right there, that's essentially initiating a calculation that's going to give us 3 waveforms. But basically that's the position versus time, that's the velocity versus time, and that's the acceleration versus time. And so this function that I created that's generating all this, I can assure you that that times that is the derivative of that incoming signal. So this is one of my favorite libraries, Terry's Electrical and Mechanical Components, which really means that this idea that the way I'm dragging and dropping blocks, you can create your own, and those are usually the most useful ones, because those are the ones that really you built up to match your own kind of components that you continually use from one project to another. And so as you put together the Simulink model, what we're going for is that it's beginning to emulate the processes in which you actually put hardware together too, based on components. So let's see, so I created one, and I haven't used it for a while, but this guy right here.
Trigger, like from the game controller?
Okay, so this is a triggered version of that same thing, right? And you'll see the trigger comes in right here. This is doing something super simple, but it's important. It's about resetting it. So it looks like it's just going from 1 to 0, but this thing right here, you can see a rising edge kind of thing, which I think is terminology
we went from
you've used
0
before.
to 1. Yeah, it's electrical engineering.
Yeah, it's looking for that 0 crossing. Hit run, you ready to play?
Yep.
Okay, let's go.
Put me in, coach. I'm ready to play today. That seems like it's a better representation of how far I can go.
Yeah, speed doesn't really seem that bad now. And those are collisions, I can kind of see.
Oh, and the ball is pushing back on it?
So that's every time the ball hit. And these ones right there, those are probably your real good shots, because you're really getting a good piece of it and you're sending off at a pretty good velocity. So Felix, you have that working quite well now, and one of the things that looks different is you have connected to it.
Yeah, before we were working with the Teensy, and we had this board with everything broke out here, going out to the MOSFETs, and you guys wanted to demonstrate what you could do with your software and outputting some code to the the Arduino.
Exactly. We generate some, build a model, use these blocks, you see them right here, digital input, PWM outputs here and here, right? And the basic idea, as I understand it, is that that blue button on the side here is going to generate a signal, which we call digital input, and we're going to use that to essentially drive the motion of that actuator, which we would do by putting voltage across the terminals of a solenoid to make it move, right? And Ben and I were just kind of looking at the model of how all that works. Okay, so this is what Madhu did. So my colleague at MathWorks, Madhu, anyways, he created essentially a state machine, kind of a very, I want to say this in a way that the complexity of what people do with regard to state machines can be way, way beyond what we have here, but the basic concept of what these things are defined quite well with this format, and it's the idea that there are really 2 states. And in our case, our default state is the flippers right there. Let's call it its rest state even. Now the next state is that it's actually moving, and then the final state is that it's in a rest position, pointed in that direction, all right? And so our default state being right now, we really only need to be very explicit. And the 2 positions really are that it's moving, which is on the left, and that it's being held at the upper position, which is on the right. And what it means is that if we want it to move, we're going to send full voltage, all right? And that's what 255, because again, it's an unsigned integer, ranges from 0 to 255. The biggest value we can send will be 255. The medium range, which is holding in that position, that's where we send a 155. Basically the logic of what we did in this, we gave ourselves some margin for error here, and we made it 0.2. Might be interesting. We could try putting that number at 0.1 at the very least, maybe 0.05 even, and see if we're going to get the same movement on the flippers. So you want to try that? We
Sure.
can change that number and just reflash the Arduino. So let's make it 0.45. We're going to find out how well Ben and I are at doing the arithmetic of this right now. So I'm rebuilding the code right now. I'm going to hit this view diagnosis, and you get a sense of what's going on. And we're just getting a bunch of progress statements. What's taking place is that whole model in Simulink that was put together is now being generated into C code. It's being kind of mixed with the code that has all the drivers and the things that are very specific about the Arduino board. Right. But we have a block set, and you see the blocks that have Arduino on them.
File.
It's completed, so let's try it out with 0.04.
Did you do this to both of them?
Yep, seems like they still work. So Ben, I think there's some pretty good news here that maybe you and I do know how to do the mathematics of this. So.
Well, maybe. Well, let's see here. They're flipping, right? But let's see. Ah, I missed it.
So what do you think? Does it feel pretty much the same?
Yeah,
All right.
feels pretty decent.
We sure learned a lot with this project. Thanks, Terry, for coming on the show.
It was great to be here. Thank you very much for allowing me to come.
I really appreciate your expertise and knowledge.
Oh, thanks a lot, Felix. It was great to meet you too. Thank you.
We learned a lot about simulation and deploying code for mechanical systems. And hopefully we can work on things like this in the future.
That's awesome.
Well, that's all the time we have for today. We learned some great stuff from the guys at MathWorks.
If you have any comments or questions about anything discussed in today's episode, tell us about it on the Element 14 community on element14.com/TBHS.
We'll see you next time.